So, okay, so let's have a check-in with Zach to see if he's ready. And yeah, so see if the thing is okay.
Okay. So I'll see you later.
Hello, Zach.
Hi, can you hear me?
Yes, now we can hear you. So,
Oh,
yeah.
terrific.
Yeah, there was some technical issues, and we always have technical issues. Don't worry. Our house hasn't burned down, so that's fine. So yeah, how about you take us away with your talk? What the Struct?
Yeah, what the struct? Okay, so I'm gonna try this. I'm gonna try to hit the big screen. Let me know if you can see full screen the title slide here.
That's awesome. That's amazing. That looked good. Yeah.
Okay, perfect. So my talk's called "What the Struct." I'll go ahead and jump into it because I know we're a little bit behind schedule. First, a brief introduction of who I am. So my name's Zach Anglin. I'm the director of AI engineering at S&P Global. I describe myself as a Python fanatic. I've been using Python professionally for about 5 years, as an amateur a little bit longer than that. And I'm also a new dad. So I had my first kiddo about 6 months ago. His name's Malcolm. And like any new dad, I will make you all look at photos of him. So here's Malcolm last week at the Thanksgiving holiday here in the US. But enough about me. I would like to talk to everyone today about like kind of maybe a mundane topic, one that doesn't get a ton of press in the modern Python world. But I want to talk about record data types, or what we might call structs. So structs come to us from C, from the C legacy that Python has. I know everyone's familiar with it, but C, of course, is a minimal programming language. Interestingly enough, the reason it's called C is because it came after the language B. C is procedural, which means it has no objects. Everything just runs top to bottom. And so if you want to write a basic C program that would, for example, calculate the area of a rectangle, you would declare two integers. One's the length, one's the width. You'd multiply them together, and then you print that out. So here our area would be 20. But if we want to do that for two rectangles, well, we'd have to declare the first length and the first width, and then the second length and the second width. And then we have to calculate the first area and then the second area by multiplying the right numbers together. Then we'd have to get the area difference, and then we print that out. So here the area difference is 22. And you can see how as you're getting more and more complexity here, you've just got more and more variables to keep track of. And a big improvement over a program like this can be made using the struct feature in C. So in C, you can use this syntax to say, okay, well, here's a little basic compound data type that is going to hang together. It's called a rectangle. It has two integers. One's called length and one's called width. So if you do this, then you can, rather than keeping track of individual variables and making sure you have the right one going together, you can just declare this compound data structure, which again is just a collection of primitive data types, collection of ints, where we got a first rectangle, a second rectangle, and then we can access by name the length and the width attributes from those rectangles, get their areas, and then subtract them to get the difference. And this is a big improvement, but we can actually go a little further, right? Because now, rather than just manually getting this repeated area calculation, we can define a function, and we can say that function takes a rectangle struct. And now we can sort of enforce some safety here, where you're not going to calculate area on something that isn't going to have a length and a width. So now, rather than manipulating the individual elements of a rectangle, we can just declare them and then call the area function twice. And we can even get a little bit more structured than that if we declare a second struct, one that is actually a struct of structs. So this one just contains two rectangles, and we'll call that one rectangles. And we could declare a second function, so one called area diff, which takes a rectangle struct and then calculates the area on each of them. Well, now we've got basically maximum structure here, right? So this is very reusable code. There's almost no hard coding other than the initialization of the two rectangles here, and everything's just function calls. So using a struct, even in a very minimal language like C, we are able to get big wins for structure, big wins for readability, and big wins for reusability. A brief aside on structs and memory usage. C variables tend to be stored in specific memory addresses. So if you use a struct, you can ensure that lots of variables that you have together are all being stored at contiguous locations. So they're all sequentially stored in memory. And then you can read and write the whole struct in binary as a single unit. So either into memory or into disk. So that's a big win in C, but maybe doesn't apply so much outside of there. So moving out of C and into Python, we also have a struct module. So taking a look at it, a struct is a Python module for unpacking and repacking structs that are stored as binary data. It's only really useful for really high performance code. We want to take advantage of that memory performance we talked about a second ago, and also interoperating with C. And it requires declaring something called format types, which I'll get into here in 1 second. Just to give you a taste of what it looks like, here we can say, okay, import struct in Python, and then we can use this struct.pack function, declare this HHH, which I'll get to in 1 second, and say, okay, well, we're going to pack the numbers 1, 2, and 3 into binary. And if we do that, we'll get this binary object where we can see we've got a 1, a 2, and a 3 sort of scattered around these bytes in memory. And we could write this to disk, we could serialize it, but we've got this packed struct, which is actually equivalent to what it would be in C. And this HHH is that format string that I alluded to earlier, which is a domain-specific language for struct, which corresponds to this table here. So in this one, we used the lowercase h, which is a short. So it's an integer which takes up 2 bytes of memory. And if we were to come back here and change that HHH and say, okay, well, rather than using a short, let's use longs, well, we're going to wind up using a lot more storage for those same 3 numbers, 1, 2, and 3. This is why the struct module is really important if you want to be you want very fine-grained control over the exact amount of memory or the exact amount of disk that's being taken up by your data structures. Outside of that, there doesn't tend to be a lot of usage of the struct module in Python. Similar to integers, we can do the same thing with characters. So if I wanted to store as a binary struct the letters of my name, Z-A-C-H, well, I can say use the format string CC, and then I'm going to get this binary string Zach. And I can also unpack binary. So just like I can pack to binary, I can unpack from binary using the same format string. So if I pack up the letters of my name and I unpack that to a new variable called unpacked struct, well, that's going to give me a tuple of each of the characters in that struct. In this case, again, the letters of my name stored in binary. Now, looking again at this, it is of class tuple. What we got out of the struct was a tuple. And I just want to zero in really close on that because it's key to the rest of the presentation. This is what I would call a what the struct moment. Because if you recall, the whole point of using a struct in C was that we got this reusability by being able to access into the attributes by name of the struct. So we got to actually call the length name to get that first element of the rectangle struct. But if we're in a tuple, the only way that we can get into the elements of the tuple is by indexing. We lose all of the names that the struct got us in the first place. So there's this major piece missing that actually gave us all of the reusability in the compound data structure that a struct offers. So this is kind of a problem. And the solution one of the first solutions that Python offers to it is called the named tuple. Name tuple is stored in the collections module. So you got collections.name tuple, and it's pretty simple. It's a tuple with names included. Just showing how we can use a name tuple to pull out the data in a struct. Well, if we take that same, the letters of my name, packed and then unpacked, we can also declare, it's got this funky syntax, declare a name tuple where we say, okay, well, here's the name of it. And we have to repeat this twice. That's for pickling reasons. But we can just use a string limited by spaces. We say first, second, third, fourth. And now we can use star notation to unpack that struct into the name tuple, and we keep our names here. So the name tuple gives us back that freedom that we had in C to actually index into the data structure and use the names of the individual attributes. Now, yeah, so as we're doing that, right, we can now access individual elements of the struct and say, well, print my name.first, my name.second, my name.third, and see each one of those individually. The constructor for a named tuple is, again, kind of weird. So you say collections.name tuple, you have to say the name of the type, and typically that needs to be the same as the name of the class that you're creating. And then you've got this space delimited string for the field names. It could also be a list, but most frequently for the collections.name tuple, I see that space delimited string. And what that does is it creates a subtype of tuple named whatever you call your type name. It inherits all of the methods that you have on tuples. So anything you can do with tuple, you can do with a name tuple. And then it gives that named attribute access to the fields in the tuple. But it's still a tuple. It's still immutable, like tuples are. It has the same memory footprint. So there's no dunder dict attribute underlying the object, and it compares equally to a tuple. So taking a look at each one of these, here's a basic name tuple called name. We got first and last. I can create one for me and pass it my first name, my last name. If I print it, I get a nice repr, much nicer than if I got just a tuple. So it shows me what the first name is, what the last name is. If I alternatively just create a regular old tuple, my names, well, I don't get those names, but if I compare the two together, I say, well, me as a name tuple versus me as just a tuple, those actually compare to being the same thing, which is a nice feature because you're not losing anything when you cast from a tuple to a name tuple. You also have the ability to add default values. And again, the syntax kind of gets a little funky. Here, if we say, well, name's going to be a name tuple, and we're going to add a middle name optionally after the first and the last. And by default, if that middle name's not provided, we're going to say it's X. And now if I instantiate a name tuple for myself and I leave the middle name off, then I'm going to get a name tuple. It's going to include the middle name, but the middle name is just going to be X. And it's worth digging into how exactly you need to declare these things. So consider if we have a student name tuple, and the student has 4 attributes: a name, an ID number, an age, and then a year in school. And if we define 2 defaults, 10 and 5, well, what's going to happen here is we have 4 potential fields and then 2 named defaults. Those defaults, because anything that's not provided has to come after in Python, just using the syntax of an initializer, has to come at the end of the things that don't have defaults. So they're going to get tacked on here onto the last 2 fields. So if I instantiate a student name tuple without providing the age or the year, then I'm going to get the age and the year provided by this 10 and the 5. They'll only correspond to those 2. If I didn't provide a name, well, then I wouldn't have a valid name tuple. So another feature of the name tuple is the ability to create a dict. You can generate a dictionary comprehension or a dictionary representation of a name tuple using the _as_dict method. So if I just create this Tommy name tuple and then I call the _as_dict method, then I'm going to get an ordered dict of all of Tommy's attributes and all of their values. And finally, the name tuple, just like the tuple, is still immutable. So I can access the Tommy age attribute. But if I want to say, okay, well, Tommy.age, rather than being 10, I'm going to make it be 11. Well, that's going to throw me an attribute error. And the reason is, again, tuples are immutable. They're actually immutable at the C level of implementation. So as an alternative for attribute modification, we have a method _replace that lets us go in and generate a new name tuple with some modified value. So if I actually did want to say, okay, well, Tommy's not 10 anymore, Tommy's 11, then I can generate a new name tuple, Tommy +1, where I call the _replace method and I say assign the value 11 to Tommy's age. And then I can see, well, in the Tommy +1 name tuple, Tommy's going to be 11. But in the original Tommy tuple, this can't change. It'll always be the same. Now, looking at the name tuple, it's an improvement over a regular old tuple, and it gives us that key feature of being able to reach in and store attributes on the structure. But what about types? So if you want to assign a type to name, for instance, you really can't. You can't say, well, name is expected to be a string. For that, you've got another option, another implementation of the name tuple in the typing module. So the same object, the same feature in the language, just in 2 different modules. This one is in typing. So that was introduced in Python 3.6, maybe 3 or 4 years ago. It provides a structural subclass, an actual inherited subclass of tuple with typed fields, and it introduces this class-based declaration syntax. That syntax is optional. So just like your collections name tuple, you have a one-liner declaration where now instead of using this string, you can actually pass a list of tuples where the first element is the name of the field in the name tuple. The second element is the type, and then you're going to get type annotations on each of these fields. But that's again kind of a weird syntax, a weird declaration syntax, and so it's a lot nicer to use a subclass. So just like you would for any other structural subclass you're going to create, if you import name tuple from typing, you could just subclass it, declare a class. You don't have to define an init method. You don't need to mess it with self at all. You just say, okay, well, here are the attributes, here are their types, and then you've got the exact same structure, but it's a lot cleaner and easier to read. And also now, if you want to add default values, the default values before were kind of confusing, and we had to figure out where they're going to map onto the unpacked fields. So now, if you're using the class inheritance syntax, it's a lot easier to read. You just say, okay, well, age default equals 10, year default equals 5. That is a whole different degree of sanity as compared to the collections.name tuple implementation. And finally, if we want to compare with a tuple, we say, okay, well, Tommy's going to be a student. Tommy's got name Tommy, ID 1, 2, 3, 4, 5, age is 10. He's in the 5th year in school. That's going to compare exactly equivalent to just a regular old tuple. Now, this is a nice feature, but it's kind of a double-edged sword. If you're comparing a name tuple, which is this class that you define, where each of the values of the tuple has a meaning. And to just illustrate that example, if we had another name tuple that called a car, where the car's got a color, it's got a vehicle identification number, it's got some number of wheels and some number of tonnage, and we've got Ginger, who's a person, and then a pickup which has the color of Ginger, but all of these values are the same. The ID matches the VIN, the age matches the number of wheels, the year matches the number of tons. Well, in those two, even though they're different classes, right, they're different types of name tuples, are also going to compare equivalent. So it's nice to be able to compare with a regular tuple value until it isn't, because here there are very little applications where you would actually want a student to compare equivalent to a car. And lastly, just like we had in the collections.name tuple, we have immutability on the attributes in the typing name tuple. So if we try to say, well, Tommy's age is 11, we'll get this can't set attribute error. So when would you use named tuples over a regular tuple? Anytime I'd say you want to add structure to processed immutable records, if you want to give descriptive names in compound data types, and to get rid of those magic index numbers. I think a lot of times when you're refactoring code, you can see, well, we're going to take this tuple and just the third element out of it. We're going to pass that along to some downstream function. You can really improve that by assigning names that are descriptive and conveying to anyone who's reading the code what actually the third element of the tuple means. Now, when would you use typing name tuple over collections.name tuple? I'd say here basically all the time. I think typing.name tuple is Pareto dominant over collections name tuple. And if not all the time, I'd say at least when you're working in a typed code base. And also please work in typed code bases. Now if we're just saying, well, what other representations of structs are there? And there are actually a lot of them in Python. And the objective of this talk is to give kind of a survey of what the different options are and what the different use cases might be. Exiting tuple land, the next obvious choice is a data class. Data classes were introduced in Python 3.7 about 2 years ago. They offer a shorthand for creating lightweight classes, and they create independent types. They're actually full Python objects with no relation to tuple. There's no inheritance going on. To give you an example of a data class, we can say from data classes module, import the data class, and then use that as a decorator on some regular class definition. And you'll notice this looks actually identical to the typing.name tuple. The only thing we changed was we're not inheriting anything, and we're using a decorator to say this thing's a data class. And if we initialize one, we get the same default values. Tommy's going to get age of 10, year is 5. And one difference from the typing name tuple is that we're not immutable anymore. So if I want to say, well, Tommy.age increment by 1, well, Tommy's age is now going to be 11, and I'm not going to get an attribute error. Which, depending on your use case, maybe that's a good thing, maybe it's not. Conversely, I can't now index into any of the attributes that are stored on the student. Apologies, I think my puppy saw someone at the door. So unlike the raw tuple, I can't just say, give me the third element on Tommy. You can only access them by name. So if I try this, I'll get a type error and say student object is not subscriptable. So just to recap, a data class is mutable by default. It's not subscriptable, and they are just plain Python classes. And because they're just plain Python classes, you can tag on a method here. So I can say on student, rather than accessing the attributes directly, we could declare a birthday method and say, if you call birthday on student, then age is going to increment by 1. And we can just call Tommy.birthday rather than adding 1 to his age and get that same age equal 11. Comparing with a tuple, it doesn't work at all, because we don't have that same inheritance from tuple that we got with the name tuple. So if we declare Tommy here and then compare him to a tuple with the same attributes, that's now going to compare to false. However, if we wanted that to be the case, we wanted that comparison, then we could say call dataclasses.asTuple function on Tommy, and that's going to get a tuple representation of the value stored on Tommy, and that will compare to true. You can't emulate immutability with a data class. I'll get into in a second why I say it's emulating. But if you declare a data class and say frozen equals true, then that's going to throw an attribute error anytime you try to access or modify one of the attributes on the object. So here's a frozen point. I'll say, well, the origin is at 0.00. And if I say origin.x plus equal 1, that's going to throw me a frozen instance error. It's going to say you can't assign to field x. The reason that it's only emulating, it's not actually immutable, is that this is a full Python object. So there is this dunder_dict attribute. And if I go in and say, well, origin dunder_dict element x doesn't equal 0, it equals 1, then even though the data class is immutable, or is supposed to be immutable, it's frozen, I'm still going to be able to access that attribute. And that's not the case for a name tuple. So a data class is a Python object, and all Python objects have this dict attribute, which stores the attributes on the object, whereas a tuple is a C artifact. So at the C level, the tuple is an immutable structure itself. So there is true immutability for a tuple, not for a data class. So I'd say if what you want is a simple tuple, then you should use typing.nameTuple. And if what you want is a Python object that can grow in complexity, you should use a data class. I find myself more frequently using data classes than name tuples, partially because I find that really rarely can I specify in advance what the entire use case of one of these objects is going to be. Oftentimes I'll want to add some functionality in the data class just because it's a regular Python class supports that. One of the nicest features of the data class is this dunder post init method. So if I create a data class, say I'm still working with point, and I want to say, well, I've got x and y, and I also want to say, well, there's a potential magnitude on the point, which would be the distance from the origin of some vector that would use that would go from the origin to the point. And if I say init equal false on the field of that attribute, then I can use this post init method and say, well, after we run the init, after you initialize this point, then actually set magnitude to be the square root of x squared plus y squared. Now I can create a point with x and y of 3 and 4, and then whenever I initialize that point, it's automatically going to calculate and store this magnitude attribute. So I get 3, 4, and magnitude equal 5, all on this class for free without having to specify or say that it has to be calculated. If you want to learn more about data classes, I would really recommend Raymond Hettinger's the Code Generator to End All Code Generators talk from PyCon 2018. He goes into much further detail than I do, and I think it's the best resource that I've found. So moving on, there's also in the standard library, the typed dict. Not a whole lot to say about typed dict. It came out last year in Python 3.8. It adds typents to the dictionary object. It doesn't define a new runtime class. At the runtime, the class is still going to be a dict, but it's really useful for type checkers like MyPy. So an example of usage, it looks a lot like the name tuple. So to declare a new type dict, you say, you declare a class, you inherit from type dict, use the same syntax to say, here are the attributes, here are the types, and say, if I wanted to create Tommy, if I print Tommy, I just get a regular old dictionary, and I can even assert that Tommy is an instance of the dict. When would you use type dict? I'd say when you're processing dictionaries. So for example, in JSON, it's nice to be able to add a little bit more structure and typing to support something like a MyPy type checker. And if you want to just add more structure to your regular dict type annotations, type dict is a good choice. So moving away from the standard library, there are two other options that I want to talk about. I know I'm short on time. First is adders. So adders is a third-party library with a motto, classes without boilerplate. So it's lightweight syntax for declaring custom types. It's been around since Python 2, and adders actually inspired and consulted on the data classes module. So as an example of adder usage, I can say import adder, it got the same, it looks familiar from data class. You use a decorator to declare a new adder. And rather than directly saying the type of something, I use this adder.ib syntax. And here I can create the origin point. But a big feature that adders has over data classes is the idea of validators. So I can in an adder class, I could say, well, create a validator on these two attributes. And if the value is going to be less than 0, then raise a value error and say, well, this is actually a first quadrant point and the coordinates have to be positive. So now if I say origin is a first quadrant point 0, 0, it's going to throw me that value error saying coordinates must be positive. More features over data classes. It's got Python 2 and PyPy support, validators, converters. It has really nice syntax for using the dunder slots attribute on classes, which is nice if you want to have higher performance memory usage. In a handwritten class, dunder slots is kind of a pain to work around, and adders makes that really easy. And of course, there are more. It's been around for a long time. When would you use adders? I'd say when you need to support Python 2, and I have a little frowny face. I'd say when you need more advanced features than data classes can provide, and when you want to be on the absolute bleeding edge of functionality. Now, I'll pause here because I know we're at 4:30 and I had some technical difficulties. So let me know if I need to cut it here. Okay, I'm going to keep going then. I have one more third-party implementation of this kind of struct idea in Python. It's a newer library called Pedantic. I'll give you an example of Pedantic. The way you use it, you'd import this base model, and then you can subclass base model for, like, for example, your point declaration, where you've got an x as an int. You use the actual type annotation to say what it is. Looks a lot like a regular data class, and then you can create a new point. But it also includes this idea of validators. So sort of similar to adders, you can declare a validator as a decorator, and it can be any function. So it would be a class method, and you say must be positive. Again, we're still saying first quadrant x and y both have to be greater than 0. And if they aren't, if you provide like here x equals 0, then you're going to get a must be positive type equal value error. So Pedantic is a recent project. It takes advantage of Python 3.6 type annotations as a first-class design citizen. It provides strong support for data validation, and it has a full data classes API that they emulated. So you can, I'll show this. Rather than importing from the data classes module, you can import data class from Pedantic and use that as your class decorator. And rather than creating a data class, you create a Pedantic class. So here, I created a data class for Pajamas. So I can say Pajamas is a conference whose name is Pajamas 2020. The time is start time for this talk. And notice I type annotate time to be a date time type. And then I pass it a string, like an ISO compliant date string. And Pedantic is going to automatically convert that string. It's going to read it into and cast it as a Python datetime, just because of that type annotation that I provided it. Last feature that Pedantic gives that I've really become a fan of is serialization unbacking. So if I added this attribute on the conference class, say it's got a set of presentations, which is a list of presentation objects themselves are Pedantic data classes, just the name and a title, then I can put my name in the title of my talk, along with maybe another name and title of their talk. And if I want to deserialize this thing, say, okay, well, here's the whole thing serialized as just a dictionary with regular strings. Well, I can deserialize it using star notation and get and it's going to initialize the conference object from this outer dictionary and then the presentation object for these inner dictionaries. And then I can index into them. I can say, okay, well, what's the title attribute of the first presentation in the presentations list? And it's actually going to give me this my talk, what the struct. When would you use Pedantic? I use it when you need powerful data validation. Use it when you're validating external data through an API, where you do have to do this serialization, like you might in JSON, and you want to get those compound data structures. And lastly, if you're in a typed code base. So a brief recap, what we talked about here. We talked about C structs. We talked about Python structs and how they can talk to C structs. We talked about the collection.name tuple and the typing.name tuple. We talked about data classes, typing.typedict, the adders library, and Pedantic. And looking at that list, it should recall from the Zen of Python, there should be one and preferably only one obvious way to do it. I don't think that's the case for structural record types in Python, but each of them have their own strengths and weaknesses. And I hope that I was able to give you some background of how we got where we are today and what might be applicable for your use cases. All right, so that is the end.
Thank you. Thank you so much, Zach. That was a really cool walkthrough, yes, of the standard library structure. Thank you so much.
Sure.
Cool. And how are you enjoying the conference so far?
Oh, it's been a blast. Yeah, I'm grateful. Obviously, Pajamas has been remote for a while, but I'm grateful that we have these remote conference opportunities because, like I said, I'm a new dad, so being able to stay home is really nice and still engage with the community.
Cool. Well, thank you very much for showing up, and thank you very much for your great talk as well.
Yeah, thank you. Sorry for the technical difficulties.
It's all right. It happens. It's okay. Thank you. Thank you.
Yep.